session. I thank you everyone for coming to this session. I think it'll be a very interesting one. Marianne asked me to give a few words of introduction to the section on wind turbine aerodynamics. So this is my take on it. If you look at the papers that were presented at the last talk meeting at TU Delft, it was actually a virtual meeting. They divided the papers up into 8 categories, and the categories are listed as dot points here, and the number of papers for each of those categories is listed. So you can see the top 3 are by far the most popular ones. And the sort of not very inspiring takeaway message from this is that when you look at those 8 topics, they all have a significant aerodynamics components. But the follow-up thought I had from listing that is that may be true, but what are the gaps in our knowledge of the aerodynamics? And a little bit of an idea of what those gaps are can be got from looking at a couple of recent grand challenges type articles about what the research challenges are in wind energy. There was this one from 2016 organized by Gies van Kieck, and then Paul Viers and the team in 2019 produced a very detailed and quite long report. That's the second part of the reference here. And there's a brief overview of it that was published in Science. And if you look at that in terms of the aerodynamics, then there's clearly many areas where we need to do some more work. The operation of vortex generators on blades, flaps and blade erosion. And one particular thing that I'm very keen on is that I don't think we really have a fundamental understanding of how wind turbines behave. We don't really know a good formulation for modeling the flow in the high thrust region. And we're going to see an example today where that also challenges our fundamental knowledge. Unsteady aerodynamics is also an area where we need to know more, and there's a couple of presentations on that today. And of course, the interactions of wind turbines with each other in wind farms and with the atmospheric boundary layer are also really important issues, and that we're going to be touching on that as well today. So I'm going to finish there. If I can figure out how to exit and stop sharing my screen, I will do so. And I'll ask Ryan to say a few words.
Perfect. Thanks very much, David. Hi, everyone. Bonjour à tous. I'm Ryan Kilpatrick. I'm a research engineer from CanMet Energy Ottawa. And I am pleased to welcome you today to the 2nd annual iteration of the Canadian Wind Energy Research Network. Marianne, are you able to show some slides, or should I bring them up on my end? I can bring them up. That's easier.
You should be able to, Ryan. I think
okay.
Everyone has permission to, although apparently my slides didn't get shown. So what I'm going to do is put my presentation in the chat.
Okay, thanks, David. Can anyone see my screen? Does it have the slides up?
Yes.
Okay, okay.
It's in presenter mode at the moment.
Oh, it is. How about that? Is that okay?
Still in presenter mode. So if you go into slideshow, it should be right.
Well, yeah, I might. Let's try here. Sorry, just a second. How about that?
Yep.
Perfect. Okay, thanks. So perfect. So thanks everyone for joining us today. I just want to remind everyone that this research network is really a forum for that is to support the interests of wind energy researchers and practitioners in Canada in terms of advancing the state of science as it relates to the needs of the wind energy industry and its applications. One of the goals of this network is really to increase the awareness and the visibility of the research that's occurring at various institutions across Canada, and to strengthen the linkages between research and industry. So just a reminder, the Research Network plans to hold at least one meeting per year. So we've done this virtual format for the last 2 years, and we're certainly interested in moving into an in-person format in the future when it's safe for everyone to meet together. Just wanted to remind everyone who's on the steering committee for the Research Network currently. These are the members on the screen here. And I wanted to welcome Charles Goudreau from Nergica, who is a new member of the steering committee this year. And certainly as we progress through the seminars this week and next week, certainly feel free to reach out to any of the members of the steering committee if you have any questions. We're also looking for feedback in terms of the format of the sessions and the structure of the research network. So certainly would encourage your input on that. There will be a feedback request at some point for members to share their thoughts. And so just a reminder of the agenda that we have. There will be 3 webinars this week and 2 next week for a total of 5. And there are obviously different topics that will be covered, and a very interesting mix of presenters in each of those topics. And a reminder that all sessions will be recorded and will be shared with the Research Network following the meeting. I think that's all from my end. David, over to you.
Okay, thank you, Ryan. Well, we're actually on time. We've had one presentation that won't be happening. I think that's the second last one. That'll give us a little bit extra time. What we thought would be the best thing to do is, if a presentation is within the time allotted to it, then we'll take questions at the end of the presentation. Otherwise, if you could save them till the end, till we've had all the presentations. And the other thing that could be a good idea, if you've got a poor memory like me and forget what your questions are, you might like to put them in the chat, and we'll either deal with them at the end of the presentation or at the end of all the presentations. So with that, I'm going to start off, because for some reason I ended up being, I was the first cab off the rank in the listing. So I'm going to tell you about the yaw behavior of small wind turbines. And I'll try and get my sharing right this time. So if I share the screen and share that. So can you see my presentation?
Yes.
Good. Yep.
Yep, it should be in the correct mode.
Oh, yeah, there we go. Looks good.
Okay, well, thank you. This is work that I've been doing with an ex-student of mine, Mohammed Hammam, at the University of Port Said in Egypt. And it's work that is supported by an NREL subcontract. And we're going to be presenting this work at the upcoming Talk 2022 meeting, hopefully in person in June in Delft. And if anybody is interested in further details of the work, just send me an email and I'll reply with a copy of that paper. Like all the talk conferences, the papers will be published in the Journal of Physics conference series. So what the topic is the behavior of the tail fin of a small wind turbine. And that is actually an extremely important component of small wind turbine behavior, because everybody knows that your errors reduce the power output. But one thing that is particularly apparent for people involved with small wind turbines is that if you have a rotating rotor, and remember that small wind turbines tend to rotate at much higher RPM than large turbines, and that rotating rotor is yawing, that induces gyroscopic loads on the blades and the main shaft. And those loads depend on the blade inertia, the blade RPM, and the yaw rate. So yaw can lead to poor power extraction performance, but it can also lead to loads that are sometimes the maximum loads on small wind turbines. So it's very important from all perspectives. So what we decided to do, or what we have been subcontracted to do through NREL, is to develop a theory for the yaw behavior of tail fins, and combine that with the effect of the rotor on the incoming flow, and then eventually work with the people at NREL to develop a new module for their OpenFast aeroelastic software, which is specifically about tail fin behavior. We started with unsteady slender body theory because that is a simple but apparently quite accurate method of dealing with your behavior. And unsteady slender body theory is primarily written for delta wing shapes. And delta wings, because of their importance in aerodynamics, are the most common type shape that is the shape that has had most of the research done on its unsteady aerodynamics. So if we take unsteady slender body theory and we use it to work out the moments about the tower axis due to the unsteady yaw, that's what we get. You can see terms involving C0, XP, and somewhere there should be B0. Yeah, those are the geometric parameters of the tail fin. So B0 is its span, C0 is its chord, and XP is the distance from the tail fin to the tower axis. And we end up with an equation that looks like this. This has been modified from unsteady slender body theory to include nonlinear effects at high angles of attack. It includes an added mass term. Here is beta, which is effectively the yaw angle of the tail fin. So the second derivative of beta is an angular acceleration, and the aerodynamic component of that gives us the added mass. And then we have a bunch of terms that are damping terms here. We have a term that involves the time rate change of the wind speed, and here is the term which we call the steady term, because this is a term that would appear if the tail fin was stationary. And if you know the unsteady aerodynamic moments, then the resultant inertia equation is straightforward. It's just the total turbine moment of inertia times beta double dot is equal to this expression here. So to start off the analysis of the model development, we looked at the simplest possible case. And this is a bunch of experiments that were done in a wind tunnel. Different geometry tail fins were yawed at an angle of 45 degrees. For some reason, we've called it minus 45 degrees. They were released, and blue shows the experimental yaw response. The black lines show the linear model that we've developed, and the red lines show the nonlinear model. And you can see on the left that in some ways the agreement is quite good, but it could be improved. And one of the ways that we think it could be improved is to take account of the bearing friction in the experiment. There should not have been a large amount of bearing friction, but if you do the numbers, you'll see that even a small amount of bearing friction can have a significant impact on the behavior. So the red curve here is taking a reasonable account of the bearing friction. And if we do that, we get a pretty good general theory for the response. If we look at the individual terms in the equations, this becomes important because eventually we want to have the simplest possible model that is general enough for all situations. But in order to achieve that, we have to find out which terms are important. And the main takeaway from this result here is that the red term, which is the added mass term, is quite small and can be neglected, which is entirely reasonable for a tail fin in air. I haven't shown it here, but further work that we have done shows that the nonlinearities become more important at high yaw angles. Unfortunately, at the moment, there are no wind tunnel tests of tail fins at high angles to compare with. So where we're going from here is to extend the model to high yaw angles and low wind speeds, because it turns out that for small wind turbines, you really only need a tail fin when the turbine is starting. Once it's producing power, the blades themselves tend to become stable in yaw anyway. So high yaw angles and low wind speeds are a pretty big challenge that we're going to be, what we're working on at the moment. And we've arranged with Professor Francesco Castellani at the University of Perugia in Italy for him to do some wind tunnel tests that we will use to assess those models. Then what we want to do is include the effects of the rotor, because that's obviously critical. And we want to extend the model past just making it applicable to delta wings. Then we aim to work with the NREL researchers to develop a tail fin model for open fast. And a concurrent piece of work, which I haven't got time to talk about, is assessing the importance of the gyroscopic loads, because there's an upcoming revision to the IEC standards for small wind turbines. And we hope that some of this work will feed into that revision. So I think that's pretty much all that I have to say. Yes. So I'm going to open up the chat. And I think I've more or less kept to time, so I'll stop sharing at that point, and we can move on, unless there are, shall we save any questions to the end, Marianne?
I think it's up to you, David, whatever you prefer.
Okay, maybe if there's one quick question, we could address it now. Otherwise, we could leave it till the end.
I have a question, David. Will you
Yes.
consider the thickness of the tail fin? Will that ever come into play?
Most tail fins are pretty thin at the moment, so the thickness only is important to the extent that it determines the inertia about the tower axis. And that obviously has to be incorporated. But the idea there is, of course, nowadays, most tail fin designs would be put up in SolidWorks or some other software package like that. And so the tail fin inertia would be known accurately.
Thanks.
Okay. Okay, I think that has done it. So let's, I'm trying to get out of, there we go. I've managed to get out of Zoom. So let me just open up. I thought I had opened the list of the talks. Here we go. So let us move on. And let us move on to Najiba from University of British Columbia, Okanagan. So Najiba, would you like to begin your presentation?
Hi, everyone. Is my slides visible to you?
Yeah.
Looks good.
That's fine, thanks.
Okay. So I'm going to present my research project, Performance Enhancement of Small Wind Turbines via Protective Leading Edge Ropes, which is in industrial collaboration with Harrison Blade Solutions. So leading edge erosion is one of the significant problems in wind turbine industry. The eroding effects of these wind turbine airfoil leading edge, putting the blades at risk. And researchers are working to solve this problem using various passive and active flow control methods. But we are focusing on droop because a leading edge droop can protect the leading edge, while different leading edge protection can give an idea of like aerodynamic enhancement, but leading edge droop can obviously enhance the aerodynamic performance of wind turbine. Different comprehensive panel method analysis and two-dimensional steady state Reynolds average Navier-Stokes approach over 21 airfoils from different families of wind turbine suggest the aerodynamic footprints of this droop configuration. The geometry of benchmark sub-megawatt wind turbine, SARI 3 kilowatt is selected for like this project. From that geometry, we are selecting one S-series airfoil, which is S822 for our project. So there is still opportunity existing to solve this erosion problem using a passive flow control device, which can simultaneously alter the airfoil performance. The impact of the droop device can be captured by 3D large eddy simulation, where the large eddy simulation is a compromise between the detailed analysis of Navier-Stokes and the simplified approximations of Franz approach. The anisotropic behavior of these turbulent fluctuations in the nearby region of wind turbine airfoil can be resolved in large eddy simulations. So for our research work, we proceed with first. We have 10 different droop prototypes, which are used to analyze using the kubelet software. So here we can see the droop configuration D1 was selected for its higher lift and higher glide ratio. And here is a visualization of 2D airfoil with droop and 3D airfoil with droop configuration attached here in red. So our preliminary RANS approach suggests the basic idea of this effect of droop attachment with this wind turbine airfoil. So from this figure, the slide can clearly give an idea that the stall is delayed, and particularly the transition is delayed when we use droop attachment at different angles. So the droop incorporation represented by intermittency contours for this aerofoil at a fixed Reynolds number give us the idea that by taking advantage of this droop configuration, they can yield more aerodynamic performance. Next is our three-dimensional large eddy simulations. So a LES is performed of a S822 geometry with droop and without droop configuration. And the aerofoil computational domain illustrated in the slides consists of a CH-type grid, which has a structured grid. And we used 500,000 Reynolds number. We simulate the aerofoil with a flow at an angle of attack 11.19 degree. And the aerofoil unit chord is used as a reference length for the simulation. Free stream velocity and pressure boundary conditions were imposed for the inlet and outlet of the domain, respectively. And periodic and slip conditions were imposed for top and bottom and front and back sides of the domain. And the total cell numbers was 46.5 million. So the flow field of this airfoil develops in time to a statistically steady state. The temporal variation of the lift and drag coefficients are represented by these figures. We average the values after 10 seconds of flow time for our further calculation. So by at a glance, our results from 3D LES is right here. The instantaneous isosurface of Q criterion colored by U magnitude is given here. So it basically demonstrates the three phases of our flow development. So at first, the laminar to turbulent transition phase is identified. For the base airfoil, it is near the leading edge, where the droop case has the transition phase downstream the leading edge. Then we have our attached turbulent boundary layer as marked in the slide. Some hairpin vortices are also observed near the trailing edge for both the cases, and the flow gets separated fully near the trailing edge for both the cases. So here is a more clear visualization of these isosurface of Q criterion for identifying the exact location of the leading edge where the transition is beginning. So as you can see for the base airfoil, the transition is beginning right here, like near the 2 to 3% chord, where for the drooped airfoil, it starts like 15 to 20% chord location. And the breakdown to turbulence is delayed after the droop attachment in comparison with the basic SA2 airfoil. So the visualization of instantaneous vorticity magnitude can give us an idea about the span-wise coherence. So we observed some span-wise coherent turbulent streaks for the drooped case, where this span-wise coherence was absent for the base airfoil. The pressure distribution for both the cases can give us the idea of the exact location where the flow gets separated and again it gets reattached. So in this region of the drooped case, we can't find any separation or reattachment. But for the basic airfoil, we got the location of separation and reattachment as marked here. The main friction distribution also gives us the exact location of separation and reattachment, where we can also observe from the instantaneous distribution of this friction coefficient for the base airfoil, that is, the reattachment is more unstable and dynamic, where the separation is on time and in line. So right here is the separation bubble we can see from the CF distribution right here, and the amplitude of streamwise velocity fluctuations near the leading edge showed us that these fluctuations are generated due to the two disturbance mode. One is the outer mode and another is the inner mode of disturbance. While in case of drooped configuration, we just find one mode of disturbance, which is the cause of the amplitude of streamwise velocity fluctuations, which is located downstream leading edge. And transition is delayed compared to the non-droop condition, is also observed from these figures. So here comes our spectral visualization of the streamwise velocity fluctuations. So for the base airfoil, we can see like near the leading edge at 2% or 3% chord, there is a peak of amplitude here, right here, which is absent for this drooped condition. And for drooped case, we don't have any disturbance near the leading edge that is visible from the graphs. And for the second case, near the 30% location of this airfoil suction side, we can see the inertial decay law is matched right here, where the drooped case doesn't have a peak of amplitude for this location at 30% chord. The average distribution of streamwise Reynolds normal stress also depicts the location of the transition, which is onsetting near the leading edge for the base airfoil, which is delayed for the droop condition. And it's up to like 15 to 20% chord location. So in a nutshell, if we just summarize the key findings from our research project is the leading edge separation is delayed along the chordwise location of the airfoil in drooped case, and the onset of transition and breakdown to turbulence are also delayed by droop configuration. The spanwise turbulence streaks are found after transition in both the cases, but uniform spanwise coherence was observed only for the drooped case. We also gained some aerodynamic performance with 2% increased lift and 9% of reduced drag by droop configuration. And the transition is via the amplification of inner and outer mode of the disturbance for the base airfoil, while the outer mode of disturbance is caused by Kelvin-Helmholtz instability, and the inner mode can be due to the secondary instability mechanisms. The transition is via the amplification of outer mode of disturbance for the drooped airfoil, which can also be the outcome of the Kelvin-Helmholtz instability. And there is no inner modes of disturbance for drooped case. Thank you for patiently hearing me. That's the end of my presentation.
And thank you, Najiba, for keeping on time. I think, Marianne, we've got a little bit of time if anybody has some questions for Najiba. Well, while people are thinking of questions, I've got one, Najiba. The droop is really interesting because it reduces the acceleration of the flow over the upper surface. So you've got a much longer transition region than you would normally expect on an airfoil. One of the things that I thought of while I was listening to you talk, you probably know how much trouble RAN's transition models have in predicting transition behavior at these sorts of Reynolds numbers. It looks like you've got a really good test case here that you could use for development of transition models. Would you like to comment on that?
Yeah, I would like to try that too, but yeah, maybe that will be more complex, and those are more like based on some empirical relations right there for those models. So yeah, that's a good suggestion. I will.
They are. There's a lot of empiricism, but there's also very little data about it. So yeah. Okay, we've got one question in the chat, but Andrea raised her hand before that came in the chat. So Andrea, would you like to unmute and ask your question?
Yes, thank you. Thank you, Najiba. I had a question. I understood that the purpose of doing this was due to the wear on the leading edge that was causing the issues towards the turbine blade, be it in performance or just maintenance. Is this true? Because that goes to my second question as to if you were to do this droop, have you considered the impact of what that would do on the droop in terms of wear and tear and erosion, and then extending that into the materials part of that?
Yeah, thank you for your question. Like droop specifically, it protects the leading edge from that erosion. And then later on, it like gives a smoother pressure surface there and enhance the aerodynamic performance. But droop material should be like it should be more in line with the erosion. I mean, that's the first job of droop, to protect the leading edge and also itself from the erosion, and then it will enhance the aerodynamic performance of that blade.
Okay,
I hope that answers your question.
thank you.
Okay, I think we've got time for just one more. There's one in the chat. Is it possible to see the size of the turbines it would be applied to? And is there a specific reason why smaller turbines are used for the model? Would Najiba or Joshua like to comment or respond to that?
I can. Thanks for the question. The reason why we selected small turbine initially is because we found when we did boundary element method, the improvement in performance by applying any kind of droop that we could imagine on large turbine blades was very marginal, whereas the improvement in performance at the smaller turbines at lower Reynolds numbers was much higher. And so we found that case to be more interesting. Erosion is probably as important or more important on the larger turbines, especially if they're operating offshore. But the aerodynamics and the impact of the droop on the aerodynamics was more noticeable on the smaller turbines. So we started there. Thanks, Nathan.
Okay, thank you. I think we'll leave it at that because we're just about over time. So thank you again, Najiba, for your presentation. And if you could stop sharing your screen, we move on to the next one, which is Eric Lineker, who's going to tell us about performance limits and their limits on performance limits. So Eric, would you like to go ahead?
Sure. All right, let me share my screen here. Can everyone see that? Okay. Well, then let me.
You're fine, Eric.
Okay. All right. So yes, the title of my work is Rethinking Turbine Performance Limits. And the key takeaway that I hope you get from this is simply a newly hypothesized limit to consider in your own work. Now, when we talk about a turbine performance limit, the question we're generally trying to answer is, for a given swept area and for a given wind speed, what is the maximum energy that we can extract from a flow? And of course, the classical answer to this question is the Betz-Joukowski limit, more commonly referred to as simply the Betz limit, but I'll try to give Joukowski his due here. And this is expressed as a maximum attainable power coefficient, defined here, where P is power, rho is density, A is our swept area, and U infinity is our flow speed. And we get a maximum percentage here of just under 60%. This comes from a one-dimensional momentum analysis, and the predicted thrust from that analysis at that optimal power is a thrust coefficient of 8/9. Now, speaking of thrust, that brings up a second possible question we can mean when we talk about a limit, which is, for a given power extracted, what is the minimum achievable thrust on the turbine? Or we can invert that. For a given generated thrust, what is the maximum power that we could be extracting? And from an engineering perspective, this is just as important of a question because, of course, thrust requires that must be sustained by the tower. And of course, that comes at a cost. So I have an answer to propose to that question, but this is nested within a broader research question that I'm interested in, which is, how is vortex shedding in general associated with lost energy? By lost here, I mean lost to usable work. So we have two extremes, right? We can have a bluff body that is generating a vortical wake, but extracting no energy while it generates some drag. Or we could have an ideal turbine that extracts as much energy as possible, generates some drag, but is still generating a vortical wake. So there must be something different about the structures of these vortical wakes that would indicate whether energy is being extracted or not. So that's the broader context that I'm interested in at a fundamental level. So now, to present this new hypothesis, I want to give you just the broad strokes of the derivation. If you're really interested in the details, please talk to me after. I can share the preprint of this work. And so the derivation proceeds from having an unbounded incompressible fluid domain. We define a control volume that does go out to infinity. We call that domain V. And we have a fluid power device of unspecified nature embedded. Now, when I say unspecified nature, it could actually be a turbine, could be a propeller that is putting energy in to generate thrust upstream, or could even be a bluff body. And we assume that the flow began a finite time ago. So we have a growing wake of finite length. So if we assume that the device also is operating periodically, we assume that wake is getting longer every period after the other. We're also going to have to invoke the assumption that the device does operate cyclically, so it reaches some sort of dynamic steady state. So all the parameters of interest become periodic, including the appearance of the near wake. Compare this, of course, to the classical analysis from which we get the Betz-Joukowski limit, where we have a steady control volume that follows the flow moving through the turbine, which implicitly makes assumptions about the nature of the device, whereas here I'm making no such assumptions. So I start by defining the kinetic energy. U here again is the velocity. We apply Helmholtz decomposition, which we can do to any vector field. So phi here is the scalar potential, psi is a vector potential, and that allows us to split this integral in the kinetic energy expression. And applying that incompressibility condition, the divergence theorem, and a vector identity, we arrive at an expression that looks like this. So I'll draw your attention first to the second term, which, if we had an unbounded flow, but the flow decayed, the velocity decayed to zero at infinity, and we had no embedded bodies in the flow, then this would be the total expression of the kinetic energy in the flow. So I bring that up just to point out we expect this in general to be a positive quantity. Let me go back. And the first term here is a integral over the boundary, the complete boundary of the domain, including the body surface and infinity. And so the effect of the free stream velocity is going to come into play here, and it's going to have an influence on the relationship between power and thrust. Now we'll manipulate that first term a little bit more. Can't obviously show all the steps here today, but we're invoking the assumption that the device operates periodically. So then we can get an expression for the change in kinetic energy from one device cycle to the next. So tau here is the period of the device. And we have then the first term being simplified to a scalar product between that free stream velocity vector and the net change in momentum inside the domain. So of course, we can now relate this to the cycle averaged thrust. The last term is a difference in what I'm calling here the vertical wake energy term, which I drew your attention to before. And so now we have an expression for the cycle average power P bar being related to 1/2 U infinity T bar, which is the cycle average thrust, and a difference in I psi here is just shorthand for that vertical wake energy term. Where this now actually gives us a performance limit we can talk about is if we note that this second term is expected to be a purely parasitic term. And what I mean by that is that at time tau, this vertical wake energy term is always going to be greater than at time 0, or at time t plus tau versus time t. So if we move one cycle in the future, that wake has grown, we expect the magnitude of that vertical wake energy term to be still positive, yet even greater. So with the minus sign ahead of it in this expression, this term is always detracting from the available usable power. So as an ideal limit, if we just assume we can drive that through good design to be 0 or close to 0, then we get an inequality that looks like this. And if we put it in normalized form in the conventional definitions of power and thrust coefficients, the newly hypothesized limit here is a ratio between the power and thrust coefficients, and we expect that to always be less than 1/2. So this is not directly comparable to the Betz-Jakosky limit. It's a limit of a different nature, essentially. But if we try to give some discussion of these two methods, the Betz-Jakosky limit comes from, as I said, a classical one-dimensional momentum analysis that would be relevant to an actuator disk model of a turbine. And of course, so this solid black line is the expected ideal relationship between power and thrust for an actuator disk. And the peak of that curve is, of course, the Betz-Jakosky limit. This dashed line is simply the line of CP equals 1/2 CT. And so we expect, if the hypothesis holds, we expect experimental data to show relationships below this line. Before I get on to some experimental data, I just want to point out that if true, this suggests that the Betz-Jakosky limit that we're all used to is simultaneously too optimistic and too pessimistic. It's too optimistic because if we restrict our attention to thrust coefficients under 1, which we're accustomed to doing, then the Betz-Jakosky limit is not attainable in terms of the power that it predicts. Of course, if we let ourselves imagine thrust coefficients usefully generated in excess of 1, perhaps even in excess of 1.2, it is conceivable that we get power coefficients even greater than the Betz-Jakosky limit. And this would be most relevant to devices such as diffuser augmented or shrouded devices, where you have some auxiliary component that isn't part of the prime mover, but which redirects the flow in a beneficial way and sustains drag usefully in the process. So now let's look at some data from the literature. I've specifically only looked at experimental data, and it is somewhat difficult to find data that reports both thrust and power simultaneously. And we do see a general trend, as we'd expect. With increasing thrust, we have increasing max power, but we do have some data points that are superseding this new proposed limit. The two most offending studies here I'll talk about briefly are that of Krogstad and Ericsson in red, and one of the data sets from Miller et al., which is the blue circles that are filled in cyan. So I don't know if you can see my pointer or not, but I'm pointing just right here. And so part of the reason could be actually blockage. These two studies, of all the ones that I've shown here, have the greatest blockage. And so we expect power to be affected more positively by blockage than thrust. And so this could drive some data points above the line. So as a crude method of testing the effect of this effect, we can apply a blockage correction, which is based on momentum theory. So we have a bit of we're going back to the old approach in so doing. So if I apply the correction of Barnsley and Wellicombe, this is going to shift all the data points closer to the line. And you'll note that now all the data points are below CT of 1, right? Again, the momentum theory restricts our ability to predict thrust in excess of 1. So this is somewhat of a limitation. This isn't a perfect correction. But now the remaining over superseding data points from Krogstad and Ericsson, this could now be explained just by a bias in their attempt to subtract the tower and the cell drag. That can't be said for Miller et al., who made no such correction. But this offending data set does exhibit some anomalous trends. So if you actually look in the legend here, we have two data sets from that study, one at a Reynolds number of 10 to the 6 and one at 10 to the 7. And the latter actually performs more poorly and does obey the limit. So this anomalous trend, they point out that it is indeed an anomaly, and they don't have a complete explanation for it. So I would say this one data set does require some more corroboration, and I think the hypothesis still does stand and requires and deserves some further attention. So I'll just sum up real quickly. Of course, the key takeaway here is this new hypothesis that I hope you will test when you have the ability with your own data. And I hope this emphasizes the importance of, if possible, reporting both drag and power in experimental studies so that we can investigate this relationship in more detail. And again, the future work still stands to be done in that more fundamental question I mentioned at the beginning, which is, if we have this parasitic term that represents drag that does no useful work, what are the features of the vortical wake that either increase or decrease this term? And can we learn anything about turbine design by studying that further? So I'll ask you to keep an eye out. I've submitted this work to JFM under the title of Vortex Shedding and Useful Work. So I hope this will be published later this year. And I'll just I'd like to acknowledge the support of David Wood, especially financially through his NSERC Discovery Grant, and also Dr. Itoji John and Dr. Mark A. Miller for sharing their experimental data. And I guess I'll leave it on this slide, and I'll take any questions if we have time.
Thank you, Eric, for that very provocative presentation. Perhaps I could start the questions by saying, can you actually put your finger on what's wrong in the derivation of the Betz-Joukowsky limit?
That's a difficult question to answer. I think because the two derivation paths follow very different logics, essentially, the different model of the flow. One is considering pressure and velocity, the other is making assumptions about vorticity. I think one really interesting point to point out is that in an actuator disk model, we are modeling the extraction of useful energy as a sudden static pressure drop. And so we're modeling the extraction of useful work without any associated vorticity generation. So through the lens of this work, that could be part of why it is able to predict higher power for a given thrust, because implicitly it's assuming something that's just physically not possible. If we're generating some power, we're going to generate some vorticity as well.
Okay, thank you. Do we have any other questions? I suspect this stuff is, if the rest of the audience is anything like me, they'll need some time to digest it. And, but it does point out something that I mentioned at the beginning of this session. We really don't know enough about the fundamental behavior of wind turbines of any forms. Joshua, you're brave enough to ask a question. Go ahead.
Eric, can you help me understand the relationship between the periodic growth of the wake and how you allow for the wake to grow, as I understand, every period? And then viscous effects, which are going to tend to smear out that wake.
Yeah, so if I go, I'll just go back to this expression here. Well, somewhere in here, I guess. So the viscous effects are, it's interesting you bring up that point, because even in the kinetic energy balance that I've shown here and that we use in a typical derivation of the Betz-Joukowsky limit as well, we are actually neglecting the possibility of energy being transferred to the thermal energy balance, right? So diffusion is actually going to be slowly taking energy out through the turbulent eddy cascade to heat. So diffusion is going to have that effect. But of course, the implicit assumption here is that that's happening at a much slower rate than the period of the device. Regarding the fact that the wake is growing, the reason that comes into play here and not in sort of traditional analysis is because we haven't defined our control volume such that we have a steady flow inside of it. We've actually just blown that control volume out to infinity, so we don't have any momentum flux at infinity. Rather, we're just relating the thrust to the momentum change inside the domain. I don't know if that answers your your specific question or not.
Yeah, maybe I have to think about it, but thanks for the answer.
Okay.
Okay, any final questions before we move on? I don't see anything coming up in the chat and nobody has raised their hand. So thank you for that presentation, which should make everybody think. And if you wouldn't mind stopping your screen share, Eric, we can move on to Dominic Bolduc from Energica.
Hello, everybody. So I will screen my screen. Correct. So you can all see my screen?
That's good.
Good. Okay. So, well, just introduce me. I'm Dominic Bolduc. I'm an expert analyst at Energica in Gaspésie. So that now I will step a little bit more in applied aerodynamics on wind turbine. So I will talk about one of our top projects at Energica this year is so it's how we integrate the Marin Vent airfoil performance monitor on our wind turbine at our test site. So our partner here is Marin Vent, also called the Areas, which is a subsidiary part of Marin Vent, which is involved in commercializing this technology that I will talk about. We also have CDI, which is an artificial intelligence company that works with us on the other aspect of the project. And it's funded by NSERC as a applied research and development program, and by CRIAC, which is a research consortium in aerospace. So how do we detect aerodynamic performance physically on any device? So as a sailor, we use telltales, also called wind tuff. So those are little stripes of wool that we put on our sail. And so we use them as a guideline to see if the airflow is going correctly on the sail. So we adjust the angle and the twist and everything on our sail to maximize the output power of the sail. So for sure, it's used more in racing, but even in cruising, some people use them. On aircraft, they also use wind tuff during flight test to see how the flow is behaving on turbine on the wing, so they can see if there's a problem at junction of the wing and the fuselage. They can also check what is happening near to stall. Some tests also have been done with wind tuff on wind turbine to have the same information as we can have on aircrafts. One problem is when wind tuff is that except for sailboats, they are not used all the way to the life of the turbine. So we need to remove them, or itself they will destroy them. So what is the Marin Vent airfoil performance monitor? Well, it's actually a highly sensitive electronic wind tuff, which is installed on the airplane for now. So what it's measuring, it's measured the non-dimensional turbulence intensity. So it's with pressure sensor on the front side and the rear side of the sensor. We can calculate the R value of the flow. So what we will see is that the R value will be very linear to angle of attack for a portion of the wind flow. But when stall occur, if there's any disruption of the flow, the device can detect the disruption. Also note that this sensor is also heated because actually it's used on the airplane to detect stall when there's icing on the leading edge. So it's a stall indicator for the pilots. So what can it detect? Well, normally that's where I will talk about angle of attack and Reynolds number. So, but with the audience that I see, I think I don't have to explain what they're for. So actually, the APM can detect for very low Reynolds if the flow will separate, is close to separation on the extrudos on the suction side of the airfoil. It can also detect for higher Reynolds number if the flow will recirculate, if there will be a bubble or something that will be detaching at a point. This would measured by the rear sensor of the APM. And we can also measure if the turbulence, if the boundary layer is more turbulent at a certain point. So for sure, it will be caused by the increasing angle of attack, but it also can be caused by the tripping of the airflow because of shape modification caused by ice, or it could be also linked to surface roughness like erosion, or also ice that is not changing the shape, but it's just giving more bumpy surface. So 4 years ago, Marin asked Aerodynamics to see if their APM that was originally think for aerospace, to see if this device could be integrated onto a wind turbine. So we've done a very small project. It was an engage insert project. So we installed 5 battery-powered APM on one blade, on the section side of our blades, and the pressure sensors, we had like 4 levels of height, 10 millimeters up to 40 millimeters. We installed those at different wingspan. We also and different chord-wise position. We also integrated the artificial contaminant because we've done those tests during summer. So we had 40 grit sandpaper, which is the common roughness that aerospace use normally. And we also had plastic bubble wrap on the before one sensor. We've made a very short run, 3 test run, one of 3 hours, one during the night, and we just collected the data. One problem that we had is that the data was not synchronized with our data from the wind turbine, but with analyzing the data, we were able to see to synchronize it a bit. So what we've seen from this project is that there's a really the device is easily able to detect very light contamination on the leading edge. So we see on the clean blade that for R value going very low, below 0.1, and after that with simulated thrust for 40 grit, we see the signal from every level of the sensor going higher and a lot higher for bubble wraps. So we see different sensitivity of the different height of the pressure sensor. And that's what caused us to bin for a longer term install. So we've been installing those devices on each blade of our ML92 turbine. We've installed them at 80 meters from the root of the blade and at different chord-wise position. One difficulty that we need to have is this sensor is for aerospace, so now it needs cabling. So we needed to cable the data and the heating and the lightning protection because the sensor is in metal. So and we acquired the data at 10 Hertz from Marin system, but we recorded at 1 Hertz on our OSISOF PI system because the turbine actually registered the data at 1 Hertz. We also synchronize the data with the SCADA of the turbine to make sure that we are in line together. And for icing assessment, we use 2 cameras that are always pointing our blades. So we have 10 minutes pictures every 10 minutes on the turbine, so we can assess how much ice there's on the turbines. So on the left screen, you can see after an icing event, and you can also see the APM, which is on the suction side here. So the objective of the project is first to design the instrumentation. So we need to, this thing was never installed on a wind turbine, so we need to make all the design, validate the installation procedure. We were working at height, working in confined space. We also analyzed the aerodynamics characteristics during icing. So that's what I will be showing after that. And now we're also incorporating AI algorithm with CDI to see if we can get any other stuff, any other correlation that we can see with the turbine and the APM. So at this time we will also be investigating other potential applications. So for preliminary results, we can see when the turbine is running. So when there's no ice on the left and there's moderate ice on the right, the signal is really clear. So we see where we find the different time when the turbine was at the same, approximately at the same Reynolds number and same angle of attack. Note that those are estimated, the Reynolds number and angle of attack. So the signal is clear that the APM is reading something going on in the blade. And this is for moderate icing. If we do it more statistically, so you see on the right for the low sensor, which is the most sensitive one when for this application, we can see for when the angle of attack changed, that the R value for the icing is a lot higher than the one for no icing. So actually, we can see kind of a shift. If we were at the higher angle of attack, which we never see on the turbine, well, we could see probably that the R value for the no ice would go up at this time, but we never experienced those kind of angle of attack. When the turbine is stopped, it's a little bit more difficult to see if we can detect ice, because it's very difficult to find a period where the wind is very similar. But when we see it statistically, we see a clear value that the R is a little bit higher than the R value for no ice for the low sensor. During restarts, we can see on the left for about the same. Actually, it's even with less wind with no icing, and a little bit higher wind during the severe icing condition. That the turbine, when it's not ice, it's really easy for the to restart. We see for icing, severe icing, that turbine starts to try to restart 2 times. And when the wind picks up a little bit more, then it's able to restart. But we see that the R value are really high, so the turbine is struggling to restart. Unfortunately, we had a blade pitch failure on blade 1 during January, so we needed to end the test. But so we had less data than we thought that we could have. But we've seen something that we were not expecting. So actually, the R values of blade 1, which is the top orange one, was a lot higher compared to the blade 2 R value. This indicates that the turbine were not at the same pitch during those times, and that's actually confirmed when we had problem with our blade. So blade 1 was moving a lot slower than blade 2. So it was able to see this difference in performance and airflow on both blades, and actually the error signal from the turbine went on 1 hour after we detect that with the sensor. So key points that we must remember. So APM, for sure, it tolerates a lot with angle of attack, especially for our wind turbine, which never goes to very high angle of attack. It's we don't see a big difference when the flow is different. APM can detect ice mostly for this configuration with the low sensor when it's at min span. During standstill, it's a little bit more difficult to detect if there's contaminant. During restart and during operation, there's no problem. The sensor is really very sensitive. At mid-span, the APM signal is mostly affected by surface roughness and the change of turbulence boundary layer. And also APM can detect pitch symmetry, which is the thing that we didn't expect to see at this time. So next step, what we want to do is install the APM a little bit closer to the tip to see how they will react. We also want to fully integrate the sensor to the turbine controller. For this, we will need to have partners like turbine manufacturer that would be interested to install this device on their turbine. Also, we would like to demonstrate other turbine underperformance like pitch asymmetry, as I mentioned, leading edge erosion, complex terrain effect. Also, Mareva would like to develop a wireless version of the APM because, as you can see, the installation inside the turbine inside the blade for wired connection. It's not an easy task, so a wireless version of the event would be very appreciated by the industry. And yet, for sure, we want to make a technology demonstration in the close future. Thank you very much.
Okay, thank you very much, Dominic. That was a very interesting presentation. Do we have any questions? No, nothing has yet come up in the chat. Maybe I can start, Dominic. What is the power requirement for the device?
Well, the power, the most of the power is for the heating. So, but for the electronics inside, I would need to verify, but I think it's very, very few. It's not a lot of amperage, and it's on 24 volts. But mainly the main power is for the heating. So if we still want to have a powered device, a heating device, we would need at least to have one cable probably to manage the.
Yeah,
the
so I was wondering whether it was suggestive of some sort of energy harvesting device to be associated with it, but I think those power levels are probably too high.
Yeah.
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 Okay. Do we have other questions for Dominic? Okay, maybe people need to digest your presentation a little bit more. So thank you, Dominic. If you wouldn't mind stopping your screen share.
Yep.
We can move on, and the next presenter is Sebastiano Stipper from the University of British Columbia.
Yeah, let me share my screen.
Okay.
Okay. This one. Okay, let me put this one up. Does everybody see the screen?
Looks good.
Okay,
Good.
Perfect. So just to introduce myself, I'm a PhD student at the University of British Columbia under the supervision of Joshua Brinkerhoff. So I will start by saying that in order to secure financing for big wind energy project, it is demanded that an accurate a priori estimate of the produced power it's made. And currently this is achieved through low-cost engineering models, given the high amount and types of analysis required, so different wind speeds and direction, because it's not doable with high fidelity simulations such as CFD or LES simulation. So despite these models are well validated for what concerns the wake prediction, so the velocity inside the wake, some recent studies have shown that they consistently lack or are completely not able to represent the deceleration of the flow approaching the wind farm and the wind turbine, which is also known as blockage. And that's where our research, let's say, kicks in. And basically blockage can be classified into two types. So there's large scale blockage, which is triggered by gravity waves above the boundary layer. And such phenomena result from the fact that the wind farm acts as a perturbation to the boundary layer, increasing its height. And the boundary layer is thermally stratified, and this thermal stratification combined with the gravity's restoring action triggers interfacial waves, which are basically happen in the plane identified by the coupling inversion layer, which is the let's say high stable stratified little layer just above the atmospheric boundary layer, and also internal waves which happen above the boundary layer, and those waves are a 3D phenomenon. On the other side, there is small scale blockage, which arises from local pressure perturbation by the single wind turbines, and this type of blockage does not need the boundary layer to be perturbed in order to appear. So our work is trying to extend what Allers and Meyers did in 2019. So they developed this model, which is called a 3-layer model, which is able to capture large scale blockage. And the thing that this model was only validated for infinite wide wind farms, which means that basically the flow properties only vary in the streamwise direction, because the wind farm is thought as to be, let's say, infinite in the spanwise direction. So we conducted a large eddy simulation campaign in order to evaluate the model performance with finite-sized wind farms. We simulated a 5x20 wind farm under a conventionally neutral boundary layer in a 33x34x28 kilometers domain, and gathering the statistics of the wind turbine, let's say, variables such as thrust, power, and so on, but also atmospheric boundary layer properties such the velocity field average in the vertical direction. And then I will explain why it must be average when I'll talk about the 3-layer model. So for the LES, we used so we include also the thermal stratification of the atmosphere, so we are able to predict the capture stability effect. And in order to prescribe time-varying turbulent inflow to our simulation, we use what is called the concurrent precursor method, where basically there is a simulation of a portion of the domain which goes on synchronized with the main simulation. And in this precursor simulation, there are no wind turbines, and that is basically needed in order to apply source term for a certain distance at the inlet of the main simulation where the wind turbines are modeled. And this source term basically removes the wind farm wakes from being recycled from the outlet to the inlet, because we use periodic boundary condition, and also brings back the flow to the correct turbulence level at the inflow of the domain. We use the in order to model the wind turbine, we use the actuator disk model, and we include the blade geometry, the rotor speed, pitch, and yaw controllers in the model, and those are the one of the NRL 5 megawatt reference wind turbine, meaning that we do not prescribe CT value. So the blade, the thrust and the power are actually computed from the blade properties, which are basically made discrete upon the rotor disc. So regarding the 3-layer model, this is derived from 3D Navier-Stokes equation, which are first expressed in their vertically averaged form. And basically, what happens is that the boundary layer is divided into, the boundary layer is divided into 2 layers. The wind farm layer, the upper layer, and then there is the free atmosphere. So these equations, the Navier-Stokes equation, are first vertically averaged, meaning that we have a 2D system in each layer, because there is no Z variation. And then those equations are linearized around atmospheric boundary layer condition, so without the wind farm, which would correspond basically to an LES precursor, or it's evaluated using some other model. For example, here we use the Newstead 1983 model. So this is the system of equation in the first layer, which is similar to the system of equation in the second layer, except for the fact that an extra term, which is identified by this C coefficient, is needed to account for the shear stress operated by the ground, and another extra term, which is to account for the presence of the wind turbine. So the wind turbines are modeled as point forces, and the thrust at a point, it's spread onto the 2D grid using a Gaussian filter. And we compute that thrust using a wake model, which runs in the background, and basically computes the thrust. Then these equations are solved, and then the perturbation field it's found, and then we sample the velocity upstream the wind farm to update the perturbation field, recompute the thrust, and so on until the model converges. And usually 5-6 iterations are needed in order to couple the wind farm behavior and the gravity waves formation. We use a boundary condition at the top at the top of the second layer, which basically relates the boundary layer displacement eta to the pressure perturbation which is felt inside the boundary layer. And this relation involves a convolution in physical space. So it's much more convenient to solve the equation in Fourier space so that this convolution becomes multiplication. And this relation involves the G prime, which is a reduced gravity, which I will define later, and this complex stratification coefficient. And basically the complex stratification coefficient is responsible for the internal gravity waves, which are 3D, and they let's say they propagate in a 3D manner above the boundary layer, and the G prime is responsible for the interfacial wave, which propagate in a 2D manner in the capping inversion layer, which coincides with the top of the upper layer. So basically the flow behavior depends on the Froude number, which is evaluated using a bulk boundary layer velocity, reduced gravity G prime, and the boundary layer height. And this regulates the physics of the interfacial waves. There is another number, the PB number, which regulates the physics of the internal wave, which is based on the bulk velocity, again, the Brun-Vasala frequency, which takes into account the lapse rate, d theta over dz above the boundary layer, and the boundary layer height and the geostrophic wind above the boundary layer. And this number is inversely proportional to the magnitude of the internal wave, whereas the Froude numbers regulate the pattern of the interfacial wave. So when the Froude number is greater than 1, the flow is said to be supercritical. So the interfacial wave cannot propagate upstream the wind farm, and the only perturbation that we see upstream is due only to the internal waves, which always can propagate upstream. Whereas when the Froude number is lower than 1, the flow is said to be subcritical, and so interfacial wave, they can propagate upstream the wind farm. So in this slide, we on the left, we are looking at the average velocity, vertically averaged velocity profile in the first layer from the 3-layer model in blue, and from the LES in red. So in order to have this data from the LES, we had to actually point by point average the velocity values and the pressure values in the layer. So I will talk about this, let's say, comparability issue that we have between this model and what was done so far in literature, where usually the hub height value it's taken. So we are looking at the perturbation velocity from 3-layer model from the LES, and the hub height velocity from the LES depicted in black. Here are velocity profile. Each plot is a different line of the wind farm, so line 1, 2, 4, and 5. And the same thing happens on the right, where we are plotting the pressure averaged in the layer from the 3-layer model and from the LES. So regarding the pressure profile, the 3LM exhibits a higher peak-to-peak distance, and the profile from the LES is less, let's say, regular. And that could be, like, we have not a clear answer to that, but two possibilities are that. So the LES domain is much shorter, and we use the fringe region. So that one be one possibility. And the other possibility is that there is some extra blockage, which is local and happens inside the wind farm. And that's why this pressure perturbation from the LES has this, let's say, double peak that we see here. Instead, regarding the velocity profile, they appear to agree quite well. The different, I would say, is in the wake recovery rate, which is lower in the 3-layer model. And that was observed also in the 2D version of the model that was previously compared with LES by Allers and Meyer. And that could be due to the stress model, which does not account for the increase in turbulence intensity produced by the wind farm. So regarding the black lines, we see that we cannot really compare the hub height velocity with the outputs produced by the 3-layer model, because so for example, upstream, when we are outside from a wake, the average in the layer is lower than the hub height velocity, because there is a logarithmic profile. But as we go inside the wind farm where wakes are present, the average in the layer becomes higher than the let's say, velocity on the hub height plane, because obviously the wake has its minimum there. So if we don't do the average, obviously we obtain a lower value. So regarding this other slide, we can see the thrust computed from the LES and averaged in time, and thrusts evaluated from the wind from the wake model, which runs in the 3-layer model in magenta. And we also have the generator power, which agrees with the NRL 5 megawatts literature data. And then we have CT values computed with different, so that's interesting. So we have these CT values which are computed with different velocities, because our model basically computes the thrust based on the blade properties, not from a provided CT. So as output, we return the CT using different velocity values to non-dimensionalize the thrust. So the black one is using the free stream velocity value, which is the velocity value from, let's say, from the unperturbed atmospheric Wanderley state. So this is 9 meters per second. Then there is the velocity value computed from a rotor disc average 2.5 diameters upstream each wind turbine, which is the red line. And the blue line, it's a velocity, it's a CT value computed with the velocity average at the disc location. So doing an average of the disc at the turbine location. And these are the two values of the averages. So the black one is the rotor average at the disc location, and the blue one is the rotor average 2.5 diameters upstream. So the interesting, let's say, apart from the fact that the 3-layer model thrust agrees with the LES, we can make an interesting note, which is that if we must be careful when using actuator disc model that do not have the actual wind turbine geometry, but only take the CT value as input. So, for example, here in the wake model used for this study, the velocity that is used to dimensionalize the CT is the disc perimeter averaged velocity. So it means that we have points only on the perimeter of the rotor disc, and we average the velocity there from the wake model, and we compute the thrust. Whereas and we have a CT value of 0.77, and that is lower with respect to what computed by the LES, which is above 1, just because the average velocity of the LES is lower because it's average on the entire disk and also in the center where the velocity is lower. So actually, in order to match the same value of thrust, the CT should be higher. So this means that in those LES simulation where we only provide the CT value, so we have to use a different velocity sampling procedure with respect to the rotor average. So the rotor average is no good if we don't provide a CT greater than 1. And usually what can be done is to use the induction curves, the induction coefficient, to compute a kind of free stream average based on the rotor disc. So basically you have the velocity of the rotor disc and you use the induction to compute an hypothetical free stream velocity with which you dimensionalize the CT coefficient. Regarding these contours of layer average velocity, they reflect what was previously said in the other slide. So the 3-layer model it's let's say underestimating the wind farm wake recovery. So there is a need for an enhancement of the shear stress model, which is in our future, let's say future works, future studies. So we want to enhance the stress layer model in the 3-layer model. And we recently came up with another idea, which is another possible way of using the model. So this idea is to compute the pressure perturbation first, then we remove the body force from the equation, and we evaluate the velocity perturbation that we obtain with such pressure perturbation. And successively, we use this new perturbed velocity field as a new free stream velocity for a conventional wake model, which at this point would run in a non-uniform field. So we account for the pressure induced blockage indirectly by let's say modifying the free stream velocity, and upon that we run the conventional wake model. Yeah, so that's all from my side. If you have any question, please ask.
Okay, thank you, Sebastiano. Do people have any questions to put to him? Perhaps I could start, Sebastiano. Mm-hmm. Could you go back to slide 3? Because I got a little bit confused about the numbering of the layers.
1, 2, 3.
Yeah.
This one is slide 3? Okay.
Sorry, no, slide 2. Yeah,
Two,
yeah.
okay.
I meant to. Yeah.
Okay.
So, in the diagram at the right, you've got 3 layers, but you talk about layer 1 and layer 2 equations. Can you specify to me which is which?
Yeah, so this is a good question. Basically in layer 1, which is the wind farm layer, and layer 2, which is the upper layer, so the 2 layers inside the boundary layer, okay, we solve this set of equations. So the first system is for layer 1 and the second system is for layer 2. The layer 3 doesn't really have a system of equation, but it's only used to, let's say, this relation, it's the relation which is solved inside layer 3, which is actually a boundary condition at the top of the boundary layer, from which you can relate the boundary layer displacement. So the overall boundary layer displacement, which is eta 1 plus eta 2. So the sum of the two is the overall displacement. You can relate it to the pressure perturbation. And the pressure perturbation, the assumption that is made is that the pressure propagates, the pressure perturbation propagates vertically inside the boundary layer and does not vary with the height. And this is a hypothesis which is usually done in boundary layers because the pressure is not perturbed up to second order, basically.
Okay, so there's actually no large eddy simulation in that model.
No, there is not. This is yeah, it's a linear model. Basically, you do an iteration of in Fourier space to solve for this equation, but this equation are steady state. There is no large eddy simulation. This is a model which runs much faster than the LES. Yeah.
And just to finish off my questions, as wind turbines get taller and taller, what does that mean for this modeling? Okay, so the thing here is that the suggestion is to use to choose the first layer height, because obviously as an input you only have the total height of the boundary layer in an unperturbed state, which is h, and then you have to basically specify h2 and h1, which is the heights of the 2 layers. So what is suggested by Allers and Meyer is to choose the first layer height to be twice as the hub height velocity, so that the wind turbine will always be let's say enclosed in the first layer, because that's the layer that accounts for the presence of the wind turbine through the body force. And then you have the second layer, which is basically a transfer this let's say velocity reduction that you have in the first layer, let's say relates it to the velocity reduction and the pressure perturbation that you would have in the upper atmosphere. So the limit here is that when you have very shallow boundary layers, such as, I don't know, like 300 meters, that becomes difficult because you have a very shallow second layer. So the model could, let's say, go, let's say, a bit on its limits here. Yeah. Okay. Nathan's put a question in the chat. Could you talk again about the issue you were trying to model, and why gravity waves are having a negative impact? Yeah. So I'll go on this slide. So what happens is that basically the wind farm inside the boundary layer slows down reduces the wind speed, right? So in order for the continuity to be conserved, this reduction in velocity inside the boundary layer must be balanced by an increase of the boundary layer height in the region around the wind farm. So this increase in boundary layer height, what it does is that it brings particles which have a lower potential temperature up to a region where the potential temperature is higher. So this triggers a non-equilibrium condition where gravity, which basically acts based on the density of the particles and thus the potential temperature of the particles, acts as a restoring force and tries to restore equilibrium. So there is a kind of oscillating motion that takes place, and this oscillating motion induces pressure perturbation. And so those pressure perturbations, which are, let's say, created above the boundary layer, propagate inside the boundary layer. And what happens is that
a pressure gradient inside the boundary layer, let's say XY, let's say horizontal pressure gradient inside the boundary layer, can actually change the behavior of the flow inside the boundary layer. For example, by slowing down the velocity, the flow particle which approach the wind farm. And as a consequence, the wind turbines would see a lower free stream wind speed than expected. Yeah.
Okay, thank you.
Yeah.
Do we have any other questions? Okay, well, if that being the case, if you wouldn't mind stopping sharing the screen, Sebastiano, and we move on to what will be the last presentation, because what was scheduled as the second last presentation by Leandro Estival is not going to occur. So we can move on to the last presentation from Rad Haji. I hope I've pronounced your name correctly. Rad, are you able to share your screen and start your presentation?
Can you hear me?
I can hear you well.
Okay, great. Okay. I hope everything works. Yep. Okay. Oh, this is the last slide.
Yeah, it's always a good idea to start with the first one.
Yeah. Okay. Good afternoon and good morning to everyone. My name is Rad. I'm a PhD student at the University of Victoria under supervision of Dr. Grant Crawford. And today I'm going to present my work, which is still in progress, is the data-driven target models for wind turbine aerodynamic simulation. So I'm going to present this work, but it's also sort of how we work on things and then how it has been progress in the last couple of years. What is when we started this work, the motivation of the work was the fact that so we have to talk about what is a surrogate model and why a surrogate model. What a surrogate model is actually a statistical model that you use instead of your actual deterministic model. The idea is using the surrogate model to have a better understanding about the statistics of your deterministic model while you run it faster. Why we are still using that? Because in normal condition, especially for wind turbines or any other physics-based model, what we have to do if we want to know what's going on in the output in terms of statistics, we have to run our simulation many times. It's expensive, but if you build a surrogate model, which means taking some samples smartly and then build a statistical model on that, and then running that one, which is much cheaper to run through a Monte Carlo simulation, we can understand what is the distribution, what output distribution much easier. And that can be useful for different topics. It can be useful for your optimization. It can be useful for load calculation for our case, or different topics that we can talk about that later. So in previous work, what we did, we tried to build a surrogate model based on polynomial expansion on every time step. It means we run a limited number of simulation, we fit a surrogate model on each one, and then we run that surrogate model. And we saw we can get some promising result, but the problem was we were losing the autocorrelation in the data, which this autocorrelation is important for us as wind turbine engineers. Before we go further, what I have to say is this work is more into mid-fidelity simulation. So I'm not dealing with CFDs, but I'm not dealing with something very large in terms of wind farms. I know we can use CFD for wind farms. This is a work that the point is using commercially available data, commercially available simulators for wind turbines like FAST or BHAWK or HAWK or Bladed. So what we see here is mid-fidelity, this aeroelastic simulation. Going back to this work, the problem was we are losing autocorrelation, which is important for us if we want to calculate the fatigue loads on a wind turbine. So we decided to change the method that we were using in order to incorporate the autocorrelation in our that we have in the time series. We decided to use a proper orthogonal decomposition in order to reduce wind field, and then run the simulation based on that, and then go through a non-intrusive data-driven method to build a surrogate model and run more colorless simulations. So in theory, it looks very good. And then here, this is the actual part that we're going to talk about today. So running the elastic simulation or dynamic simulator in this case, because we haven't worked on fast yet, we are using a package in Python right now. Getting the results, building the surrogate model, and running this mode color simulation. So when we start that, so what do we mean by data-driven method here? We are talking about the POD-PC. POD stands for proper orthogonal decomposition, and PC is polynomial chaos expansion. We are trying to mix these two together. What we are trying to mix these two together, the reason is the PCE part is going to take care of randomness that we want to take into account from unsteady winds, and the POD part is going to take care of the autocorrelation that we want to keep in the time series. Combining these two is going to give us the possibility to build a surrogate model that can give us time series as the output in a quite fast when we sample from a random domain. This is the way that we implement this. So we sample the random phases that we have. So we have to maybe go back. I don't know how deep I should go, but the wind field that we use in wind turbine simulation is an inverse Fourier transformation that we get the frequencies from the K-model spectrum. The way it works, it takes samples from that spectrum. It takes samples from the random domain, put them together, generate time series, and then we use those time series to calculate the loads on a wind turbine. Here we take the number in TurbSim, which is the commercial wind box generator from NREL. That one takes thousands of random variables at the beginning, which when you talk about taking into account, talking about uncertainty quantification, that's too much. You face curse of dimensionality very quickly. So we end up with a reduced model, which you can take, it gives us more or less the same statistics with 10 random variables. So here we start with taking 10 random variables, taking into the reduced TurbSim, which is what we call it. And then for one simulation, we take a limited number of realizations. This means limited number of 10 random variables that we take. We calculate the loads on NREL 5 megawatt rotor. And then we take it through the proper orthogonal decomposition. Output of proper orthogonal decomposition is a set of modes. It shows how the energy is distributed on different number of modes for time series. Then we project the thrust on those modes. Using the what we get as the output, we calculate the coefficient for our polynomials, and then we put them together, and we're supposed to have an autocorrelated surrogate model. So in theory, it should work quite beautifully, and actually it works pretty good. So if you look at the initial results that we had, this is for polynomial order 2. It's not that much of high polynomial order, so it's easy to fit. It's not that expensive. It is based on 30 realization, so 30 simulation of PEM. Again, competition not expensive. And the thrust from the simulation, from BM simulation, and from surrogate model matches very good. Also, statistically, it matches very good. However, this is the same data, so it is the data that I use for training. If I use the data for validation, the problem that you face is not accurate. So if I put a new time series, which was not, I didn't use for training, and then run my simulation, we can see that the statistics don't match and the time series doesn't match. And why it is the case? It is the case because the problem that what we see in our output as thrust or torque, the energy is distributed in wide range of frequencies. So you need a large number of modes in order to be able to build the surrogate model. And when we go to that large number of modes, you hit the curse of dimensionality very quickly. Curse of dimensionality means you're going to have large number of coefficients that you have to calculate. And then actually building the surrogate model doesn't have any meaning anymore, because the computational power that you have to put in order to do that, it doesn't worth it. Another reason that we have this challenge is we have this constraint of linearity and orthogonality in proper orthogonal decompositions. What it means the POD or proper orthogonal decomposition is the modes in POD, they are orthogonal to each other. And the linear combination of them is going to give you the actual signal. And these two, they're beneficial, but it means also a constraint that by removing that, you probably can reduce the number of modes that you need. So think about these things, we started thinking about, okay, maybe we can go towards more data methods, like neural network methods and deep learning methods. And we have started working on them and doing some tests. What we are thinking about is, first, as we talk about the win time series, and we said in order to generate them, you need a large number of random variables. And we are thinking about using autoencoders in order to reduce any win time series that we have. For example, if we get a win box, what we call it, from a measurement data, from measurement of a med mass, we should be able to put it through this neural network and reduce it to limited number of reduce the dimension of that win time series to a limited number of nodes. That's one thing. Another thing is we are hoping, but using neural network, we would be able to remove the orthogonality and linearity constraints. So we would be able to reduce, again, the dimension of the data that we have to a smaller number of nodes. We did some initial tests. We haven't got to the point that we can reduce the win time series, but we did some initial tests to see if we can map the data from TurbSim, the win time series, to the torque and thrust. So the surrogate model that I'm going to present here is actually mapping the win time series to the thrust and torque that we calculate. It is more or less you are trying to put a box around this part and see if you can reproduce what you have. The thing is, right now, or the model that we're using is not as complex as what you see in FAST or elastic simulation, but at least at this point, it shows some promising results. So this is the network architecture. It's a convolutional 1D network. It's very simple. It took 60 simulations, 6,600-second simulations, 20% validation, and then 80% for training. It went through 5,000 approach, and then the training time was 5 minutes and 16 seconds. This is the loss that we saw in the training procedure. So the loss went quite low. So it shows promising result, and this is what we saw in terms of error and model error for torque and model error for thrust. It's a pretty good match. So we can see that the result after 1,000 epochs is matching pretty well for normalized turbine thrust and what we have to see in the result. And then I did some predictions. So what I did at the next step, I took a new time series that I didn't use for my training. I put them through this neural network and I checked the result. So again, visually, it looks like we have a good match in terms of simulation and neural network output. In future work, what we want to do, we want to working towards working with variational autoencoder for win time series in order to reduce the dimension and also to start generating wind. So instead of using TurbSim to generate wind time series, we want to use our own variational autoencoder. The reason behind that, if you're doing that, if you succeed in that, we're going to have access or we want to have the ability to control the random variables that we put in. Next step is building surrogate model using the deep neural network, using the reduced wind that we have. So it means that you actually, instead of putting the time series into that, you can put the random variables into your surrogate model and get time series out. And also, after building this, what we want to do, and I think what is going to be beneficial for or sellable, sort of beneficial sellable for research and also industry, is using aeroelastic code output to train the network and also do the predictions. Yeah, so in time, and yeah, that was it. Thanks for your attention, and looking forward to your questions.
Okay, thank you, Rad. Do we have any questions? Okay, I'll ask you one, Rad. When you use proper orthogonal decomposition, the practical value of it seems to depend a lot on how few a number of nodes or modes you need to get a good representation of the energy, or whatever the equivalent of the energy is. So what's the situation in your use of it? Do you capture most of the information in a few number of modes?
Unfortunately, no. For POD, if you want to capture 90% of the energy, you have to go up to 150 modes, more or less, which defeats the purpose. So it's not actually reducing the dimension that you're looking for.
Okay, and so is that one of the reasons why you went to neural networks?
Exactly, yeah, that's one of the reasons, because as you go higher and higher, when you go higher on your number of modes that you need, when you do this POD PCE, then you end up at a larger number of polynomials that you have to estimate the coefficients, and that you hit the curse of dimensionality very quickly again. So that was the main reason, one of the reasons actually, moving towards neural networks.
Oh, yeah, okay. Do we have any other questions for Rad? Well, if people are still thinking or still digesting what you've said, Rad, thank you for your presentation. We're finished the presentations now, and I think, Marion, we have about 25 minutes before the session is due to close.
Yeah.
Okay, so this is the opportunity, if anybody has any questions that they've thought of after the speaker spoke, or would like to take the opportunity to network. I saw there is some networking taking place in the chat, and that's fantastic, because this is precisely what these sessions are meant to engender. So please take that opportunity. Ryan, did you want to make any comments generally about the presentations and about the network?
I don't have any comments at the moment. I just want to thank all the presenters again for their very, very interesting work. I guess if there's definitely an opportunity to highlight any publications that you have recently, and to share those with everyone here as well. So just wanted to mention that. Yes, and thank you also to the organizers, Marion and Ryan, for making this possible. Yes, so there's some more connections coming up in the chat. So Sebastian, there's a message for you. I'm going to ask a very nerdy technical question to Najiba and Joshua about their LES. But I'm fascinated that you've stretched out the transition region.
on that airfoil. I mean, it sort of stands to reason when you think about it. If you're going to reduce the acceleration of the flow over the upper surface, you're going to do that. But particularly what I'm thinking of is that when you learn about transition in fluid mechanics courses, you're told that for a laminar boundary layer, the first indication of instability is the appearance of Tolman-Schlichting waves. Did you see any evidence of that in your simulations?
I think that the lower mode or the inner mode that Najib talked about is probably what those could be. We didn't see it in the drooped case, as try as we did to look for it. I think the boundary layer doesn't have very well. One, it's strongly accelerated at the very leading edge, which diminishes the growth of those. And as you said, the droop spreads out that flow acceleration and deceleration over a much longer area, so it's much milder. But we know we didn't see the Tolman-Schlichting waves developing in the drooped case, but probably what we call the inner mode is what those are, because it matches the mode shape that we expect if it was a Blasius boundary layer. The other comment I would probably make is, well, we have a few other things that we could have presented. For example, if we look at the shape factor distribution as the flow goes, that gives us some indication as to what's happening. Mm-hmm. That's another interesting thing that we could point out and look at. But then this brings us to the bigger question of, well, what's really the difference between Tolman-Schlichting waves and Kelvin-Helmholtz waves if you're dealing with a flow that has a shear layer like what we see in the separated flow? And I think that that's another question that would engender even more discussion. If they occur at similar frequencies and you see attached disturbances preceding flow separation, and then you see disturbances at the same frequency subsequently to flow separation, what's the chicken and what's the egg? Are those Tolman-Schlichting disturbances being transmitted into the separated shear layer and locking on to the Kelvin-Helmholtz frequency, or is it the other way around? And I have some thoughts about that, but I think it's an interesting question that probably requires more investigation.
You possibly would have to do simulations at different Reynolds numbers as well, because Kelvin-Helmholtz is essentially an inviscid mechanism and the others are heavily Reynolds number dependent. Yeah.
Yeah, exactly. Yeah, I think so.
Interesting stuff. Like I said before, is so little information available to calibrate RAND's transition models at those sorts of Reynolds numbers. I think your LES is really some potentially great test case. I hope you're working on that.
Yeah, that's the original kind of motivator. I cut my teeth in developing transition models, but more in the context of gas turbine engines for the low pressure turbine. And extending those transition models is tricky. And having only one Reynolds number doesn't help.
I think we could talk for hours on this, but other people may not be so obsessed with transition as you and I. So I do see
Curran asking a question about, in LES, are there transition subgrid models versus grid result? So we use a subgrid model, but it's not sensitive to the it's not aiming to try to so the subgrid model doesn't turn off or on depending on some predicted behavior in the boundary layer. Is it predicted to be laminar or is it predicted to be turbulent? And then that changes the subgrid model. The subgrid model has a coefficient that's dynamic because it's a dynamic subgrid model. It's a wall adaptive, actually, subgrid model. So it's sensitive to the location with respect to the wall, but it's not accounting for any prediction as to whether the boundary layer is in a transitional state or in a laminar state, and then adjusting or tuning the subgrid model. And in our case, because the Reynolds number is not so high, we have a very, very fine grid. So the subgrid model actually does very little.
If you wanted to incorporate like surface roughness or something, or bug accretion or something, is that something you could actually resolve, grid resolve with your model then? Or how
Probably
would you handle
no.
that?
No, we would have to switch over and probably relax the Reynolds number a little bit, and then we could do a DNS.
Okay.
Unless we, we try to incorporate those effects into a revised wall model, but that would be also difficult.
To change the subject, there is one question that we put in the chat that we missed, and that was from Patrice to Dominic. Dominic, excellent presentation. My question is how the sensitivity of the Marinvent device compares to the standard power curve deviation method.
Well, actually, it would be probably pretty similar, well, maybe more sensitive, and especially the power curve method that we use normally cannot predict underperformance when you hit rated power, because actually the turbine has more potential to generate power at these wind speed. So what we see is that with the APM, even when we're at rated and we're at actually sometime -5 degree angle of attack, we're still able to detect the presence of contaminant because of the turbulence of the boundary layer at this point.
Okay. Are there other questions, or Joshua, I think, has put his hand up.
This question is directed to Eric. I'm thinking now just kind of in more blue sky sense. There are energy extraction technologies that are designed to work with the dynamic vortical structures that are created. I forget what they look like or what they do, but airfoils that are designed to oscillate, or things that are kind of motivated by like studying grass that grows under the ocean and looking at those kinds of dynamic energy extraction technologies. Do you think your framework would also be useful for investigating those?
I think so. So firstly, the derivation, like I said, makes no assumption about the nature of the device. So these oscillating type devices should follow the same limit. And then if you have one device generating what is vertical wake energy, all that the derivation is saying is that is remaining in the flow, but there's nothing to prevent that then from being reversed and taken out as useful information, or sorry, useful energy. So if you had a device in the wake of the other, that would really get back to the more fundamental question of what is the structure of the wake that indicates that term is large or small. And essentially, once those vortices have been formed, can they in some sense be unformed, almost like you're unrolling them, and then reducing the magnitude of that device. Sorry, the magnitude of that vertical wake energy. Of course, then the limit, like even the derivation makes no assumption of how many devices there are. So the limit should still hold for the collection of devices, if that makes sense.
Thanks.
Okay. Sebastiano, you had your hand up.
Yes, I put a question for Rad in the chat. So it's very interesting to me using the DNN to predict the thrust from the random inflows. I'd like to have some more insight about the environment that he used to implement those things, and the computational cost of the DNN with and without training, like what times we're talking about.
So if I understand your question right, your question is about the environment that I'm using to calculate the thrust and torque on the wind turbine, right?
Yeah, exactly.
So that one I use a package with, they call it BEMUSE, BEMUSE. I can send it to you. It's developed by Rick Lupton at the University of Bath. I use that one, and then that one has its own. It is verified against FAST in his PhD, but it has its own drawbacks. We can talk about them if you want to.
Mm-hmm.
And for neural network that I'm using right now, the input is wind time series and the output is the torque and thrust. And that one doesn't take that long to train. It takes around 5-6 minutes to train on 60 simulations. So 6,600 simulations. And each simulation to run takes something around 10 seconds, 10 to 15 seconds.
And that's for a single rotor, right?
That's for a single rotor for one wind speed. So if you want to talk about like cut in to cut out, which is 23 wind speeds and different rotors, then your exponentially increases.
And are you planning to like extend the model in order to like incorporate like multiple wind turbines operating in the same space, so like waking each other, or like is that a plan of your research? Or
we are not going to talk about multiple wind turbines probably, but we definitely should think about larger wind speed range. So, and that is going to increase the number of simulation definitely.
I see. Thank you. Thank you.
No problem. Let me know if you need any of this data or package. I can send them to you.
Oh yeah. Can you please put your email in the chat? So
sure.
Thank you.
Sebastiano, maybe you would like to comment on what sort of fidelity you need from your turbine models.
Yeah, no, the problem, like it's wait, let me put the. So can you repeat the question?
Yeah, I following up from the last bit. What level of fidelity do you need from your turbine models?
So the thing is that like our model, it's actually steady state, but the thing is that we have to use since we have like in our three-layer model, which actually solves equations. So we have to incorporate the presence of the wind turbine using like point forces, which are spread onto the CFD grid. But the actual value of the force is computed like offline or like on another type of simulation by an engineering wake model. So like the actual solution of the flow and the prediction of the blockage and the computation of the of the transfer are disconnected. The only connection that there is that then the thrust force is let's say updated, taking into account for the blockage that was predicted by a three-layer model. So the way we compute the thrust could be, you know, like a wake model or also a surrogate model or any type of it, you know. And the cool thing is that I think the surrogate model would be faster, way faster than a wake model, which actually for the wake model, you have to solve a linear system or do like nested for loops, which is not so efficient. So I think like once you have trained the model and you have the model, that could be also an interesting thing. But we are not interested into time series at this point because the model is steady state. So we just need the average thrust value, which I think it's much easier to go to bring to convergence with respect to the time series. Yeah.
Okay. I'm going to ask Andrea if she would like to say a little bit about her work on turbine icing.
Oh, thank you. Yeah, so I will be speaking later in the week in the cold climate session, so I won't take up too much time, but I have a background in spending a lot of time in a cold icing wind tunnel. So physically doing and building up ice in wind tunnels. So I've published a couple journal papers on that, and if anyone's interested, feel free to reach out. But basically I was involved in doing some fundamental establishment of what does icing look like on airfoils, particularly the ones for wind turbines, and modeling that so physically in an icing tunnel as well, and doing a lot of photography on it so that we could see the change between rime and glaze ice, and then determining how do we mitigate this? How do we mitigate it under both these conditions? Do we use heating? Do we use different types of coatings? Both hydrophobic and icephobic were tested, as well as the combination of it. And so in brief, the results found that it wasn't one or the other. It was really best solved by the hybrid sort of solution between using coatings and using some sort of de-icing heating solution. Now, that comes with a lot of other questions that leads to, because of just even addressing the wiring and that would be required, and the heating on those blades and things. It's not impossible, but there's a lot of work to be done still in this area. So additionally to that, I've spent a lot of time in composite manufacturing. So building different types of materials from composites, also extending that into biocomposites, and then just how that whole industry has evolved into the manufacturing of wind turbine blades. And then how do we build wind turbine blades better so that we can place them in places such as the Arctic, which is a lot of where my research is right now, in cold climates. So it's sort of coming, I don't know, full circle from what I was working in previously to where I'm placing wind turbines for cold climate solutions now. And then I was quite interested in hearing the droop solution, because oftentimes the large wind turbines are difficult to get into remote communities, especially the ones in the Arctic, which have a lot of cold climate issues related to that. So perhaps there'll be some future in combining some of these different aspects of wind and icing and mitigating all of those concerns. So that's just a brief part on it. But yeah, if there's any questions around that, you feel free to reach out to me.
This is an aerodynamics session, but are there material issues with cold climates and wind turbine blades, or is it through the agency of icing?
Well, it was well, both. Definitely there are, because we need to adapt our materials better for cold climates, but I feel like there isn't a lot of, everything's quite traditionally done, quite conventionally done. So if you were going to put in a Vestas wind turbine up in a cold climate, people will just purchase from Vestas, and there isn't much difference to the composite manufacturing of those components for that environment, because Vestas goes back to a business situation where they're most are perhaps not in those areas, right? So I think there's work in areas to develop materials for cold climates, definitely, and how we integrate solutions to deal with icing. But I think also a lot of it is just like, can we mitigate it with better design as well? So yeah, it's not one or the other, but previously it had just been related to the icing, but I think it's growing more into evolving. How do we build better for these climatic zones as well?
And what will you be speaking on specifically this week?
I'll be speaking, I believe it's on Friday the 8th, if I've got that right. And I'll be speaking to how do we, bringing in a lot of sustainable development goals and what we're doing in the Arctic, but how are we going to think through the issues of building in an environment where our foundations due to thaw and permafrost are impacting just how we build and can implement solutions in a world that is dramatically changing due to climate change, and the impact of that on wind and where that's going. So,
well, thank you. So that's a good advertisement for Friday's session. So we've only got a few minutes left. So if anybody has any burning questions, now is the opportunity to raise them, or points that they would like to raise. I would like to make an observation, and that is that a lot of the work that we've seen presented today has actually got practical wind turbine applications in mind, and or is done with players within the industry. One of the big problems that I've always had over, you can probably guess, many years of work in wind energy research is actually making that connection. So I'm hopeful that that can be an ongoing project with the Canadian Wind Energy Research Network, because I think it's a very important aspect of what we do.
Thanks, David. Yeah, I think we should definitely keep that in mind throughout these sessions, and possibly have some more discussion afterward about how we can strengthen those linkages, certainly. And we'd like to hear from everyone with their ideas in that respect.
Yes, yes. Well, I think we've probably exhausted ourselves, Marianne. I think, well, I think we've dealt with all the questions in the chat, and people have had a good opportunity to unmute and speak. So why don't we draw the session to a close?
Sure. Thanks, David, and everybody for presenting. I loved hearing the discussion. It was wonderful, and I love seeing connections being made. That's exactly the goal for this network. So please join us. On Wednesday, we have grid integration and curriculum development. And then, as Andrea mentioned, on Friday, we have cold climate and forecasting. So yeah, please join us, and thanks again for today. It was great.
Yes, and thanks to all the presenters as well. Thank you. Okay. Okay, and have a good afternoon or rest of the day. Bye.
You
Thanks,
too.
everyone.
Bye-bye. Bye-bye.
See you soon.
Right, thank you.